Okay, everyone, welcome to TSU Prism Series Talk number 15. And today we are very glad to invite Professor Yamamoto Masa-yuki-san to give a talk. So Professor Yamamoto graduated from Tohoku University in 2001. Now he's a professor in Kochi University of Technology. And his research field is about atmosphere, ionosphere, meteoroid experiment, and science educations. So today he will talk about the infrasound, immovable overpressure wave coupled with many kinds of geophysical event in atmosphere. So let's welcome Professor Yamamoto.
Okay, so I will start my talk for you, but I'm not sure that the seminar, so that's how many participants there, and I'm not sure how is your research field, but I believe so. This talk will be effective for you for the after this meeting. So please identify my name and the university here. So my university is located in the southern coast of Japan, Shikoku Island, Suko Island, and we have the 2,000 students here and a very small university, but I believe that this size of university is very effective for the good study for the students. I have the experiment in infrasound observation with using the sounding rocket or the balloon as well as ground observation. So today's talk titled Infrasound in audible overpressure waves coupled with many kinds of geophysical events in the atmosphere. The research topic is concerning with disaster mitigation. I believe that your island, country, is also a very dangerous region for the affected by the earthquake, tsunami, or any other disaster event. So that's please identify that my research topic is directly connected with disaster mitigation. But my background is coming from the Tohoku University days. We have the sounding rocket experiments there with the collaboration with ISAS JAXA team. This is one example of the measuring the plasma density profile up to about 200 kilometers by using the impedance probe technique. It is ongoing work in Tohoku University also, but at the time I engaged in this kind of project. This is another experiment of using the plasma wave measurement by using the HF measurement tool. Also, it is held on the onboard experiments up to 750 kilometer altitude. This is also the plasma experiment. And such days, it was my 1990s at the time. So I had the student days in graduate school of Tohoku University. But I graduated 2001 and then changed into my student study in my university. I got into my university 2003, and just after that we tried to make some measurement from the ground for the meteor observation. Because of my background, another background is not the study of the ionosphere, but study of the meteor by using the amateur astronomer network. So it is also my background. For example, 2001, we have the Leonid meteor storm in the world, and we have the experiment of such observation by using the cameras. I started the pointer here. Okay, so maybe you understand that this trail is coming from the meteor, but fireball class meteor, and this is almost 1 hour or the 40 minutes illuminating in the sky, and then it makes a change of the shape, and we can measure this kind of stereo observation from the multiple site observation, so it can make such wind distribution as a mesospheric region. It is one of the result of the meteor study, and this is altitudinal distribution of the meteor train, but it the with respect to the local time. So the meteor trail is changing the altitudinal distribution because of the meteor entering angle with respect to the ground surface is changing in the time. Just after my establishment in my university's work, I restarted my work with Tohoku University team or the JAXA team with using the sounding rocket to measure the atmospheric wind. And this is an example of the lithium trail just appeared on the sky in the evening sky, and the lithium gas is illuminated by sunlight, and it can make a bright object in the sky, then changes the shape, and we can measure the such distribution of the wind up to 400 kilometers. It is a very long story we have to establishment of this kind of experimental lithium release. The lithium release canister is coming from the JAXA's technique, and from my side, I developed a special bandpass filter and the special camera to make sure that such observation from the multiple site on ground. Another experiment was, I believe that it was just before the oral breakup, at just the timing of the rocket launch. We operated the rocket launch from Norway, and this image is coming from the Sweden. We can measure the wind also at the time of the oral breakup. So such experiment we resulted the study of the ionosphere or the lower thermosphere, as well as the wind measurement. But my background for the meteor science is also going into the another project of the meteor radar. The meteor radar is coming from the amateur radio communicator technique. Someone in Japan emitted some signal in the amateur radio communicator band. It is almost 50 megahertz band, and the emitted radio signal can reflect from the meteor trail or the ionized trail. So that the plasma can be found by using the interferometry technique. So after getting into my job in my university, 2003, I just started my research work by very small amount of money with student technique. So it is some educational work in my university, but this kind of small set of the interferometer is effective for the student study, I believe. So at that time, we have this kind of receiver set up. It's almost all the items coming up from my students' development, and it can be set up on the field in our campus, and also the software is also coming up from another student's work to have the image processing software for the meteor echo spectrum and make it to automatically obtained of the meteor observation dataset, and then just distributed to this kind of map on our university over our university region. So in this experiment, we check the engineering aspect of the spectrogram information, as well as the meteor astronomy of the accuracy of the interferometric technique by very, very basic setup, as well as we check the mesospheric ozone layer to make some statistical study of the meteor echo count as one small period, and we got such data set for the mesospheric ozone layer density. Then we coming up such a situation of the three kind of measurement of the meteor at the same time. One is optical observation by using the video camera with high sensitivity. One is interferometric technique from the ground for meteor radio communication technique. And then the final one is infrasound. Infrasound is a very, very rare case of the meteor, fireball class meteor can emit the sound wave. But this sound wave is not the usual sound, but this is a shock wave because the meteor coming up almost Mach number is about 30 or more. So that's this is very, very supersonical movement in the upper atmosphere or the middle atmosphere. So it can make such sound. Then the sound can propagate from the atmosphere, middle atmosphere to the ground. So we can measure if we have the ground distribution of the sensor network. So this is a brief introduction for my talk here today, but today's talk topic is infrasound. So firstly, I introduce what is infrasound. As you know, we can hear the sound from 20 hertz to 20 kilohertz. This is we call audible sound. And as you know, in the robotic technique or some prevention sensor for the car crash, so it is used ultrasound technique of the sensory network. But infrasound, lower than our audible sound range, we don't have so much research or the development in the engineering aspect. But in the aspect of the geophysical study, it is very, very important, I believe, because such wavelength is almost a few hundred meters to a few thousand kilometer scale. So it is very widely affected on the atmosphere or on the globe, our planet. So it is very effective, I believe. So it is a schematic view of our atmosphere. We have many geophysical events. Meteorite or the meteor is one of the topic of the infrasound source, but we have thunderstorms, earthquakes, tsunamis, or the volcanic eruptions, or the cloud development, or the sprite Arabs or something related to the thunderstorms, as well as artificial explosions by chemical or the nuclear bomb just after the 1950s days. And the lower cutoff of the infrasound is described this cutoff frequency equation, and before lower than this cutoff, we have the HW atmospheric gravity waves. So I think the target of the infrasound observation is consists of multiple aspects. One is weather forecast or the alert. One is for disaster mitigation or alert. And also that we can study geophysics, astrophysics, aerospace engineering by using infrasound technique, as well as environmental study or just the effect on human health by something. Because of we have the artificial infrasound sources like the wind turbine noise recently, so that I'm not sure that it affects our health or not, but some studies say that statistically, so it affects some small bad or good effect on human health. But today's topic is almost concerning with the geophysical study as well as disaster mitigation. Almost focused on the tsunami disaster mitigation or the another topic of the volcanic eruption, something. But I'm coming from the meteor study, so that's we have the some re-entry observation of some artificial meteor coming from the solar system. Most recently, as you know, we have the OSIRIS-REx, NASA's spacecraft coming from the minor planet, and the re-entry signal was caught by our colleagues in Utah state in US. But firstly, I engaged in this kind of observation in 2006 with NASA or the JAXA people at that time of the Stardust sample return capsule re-entry over Utah. At the time, I take the DCA to NASA's airplane for the observation, and with the Professor Abe, now at the Nihon University in Chiba, we take some ultraviolet image from the spacecraft, from the airplane. Just after that, we have the Hayabusa re-entry over Australia. So it means that this is the something like the test study for our case, and this is a realistic study for our first time, and to take such re-entry event from the solar space, solar system for JAXA's case. At that time, I take my instruments on the desert region of the Umera region, Australia, and distributed them on the surface. And as well as we have the image observation for the reentry capsule because of the nighttime reentry. So this is a very, very good starry sky. It is the southern hemisphere, Milky Way, and great and small Mazellanic clouds there. And so this is the re-entry of the Hayabusa. But at the time, this is re-entry capsule. But at that time, we have the mother spacecraft also coming up into our atmosphere because of the no more control for the spacecraft at the time. So this is a very, very bright fireball, artificial fireball there. This is SRC. This is mother spacecraft. At the time, we tried to make the observation of the infrasound because of it is a scheduled event for our observation, and we take the seismometer as well as infrasound microphone on that is that region, but the infrasound microphone is very limited at the time, only 5 microphones there, and the 20 seismometer also put on the ground, and we have the coupling observation. So this is the infrasound, this is the seismic observation on the ground, and this is the coupling observation there. And we have the five seismometer on this kind of distribution, so that we have the small changes of the shockwave reaching time on the ground. Just after that, we have the Hayabusa 2 2020, but very, very bad thing is COVID-19 situation affected very bad for our observation. But the happy thing is that just before the re-entry, we have the meeting of the Meteoroids 2019 at Slovakia. And the other time we have the coffee break session. We talked to each other for the Carleton University team in Perth, and we talked to them that we will visit Perth and we will visit the Umera again to make observation for the infrasound by using the Hayabusa 2 re-entry. But it failed, so that we have the connection online, like this meeting today, and we export our infrasound observation items to the Carleton University, and the Carleton University team very, very successfully operated our observation items on the ground in desert region, and our collaborative work was successful. This is one of the examples of the Carleton University Fireball observation network. This consists of almost the unmanned camera system of the video camera for the Fireball, but they don't have the infrasound or the seismic measurement there. So some of the students there or some of the researchers there currently trying to take our infrasound sensor coupled with their image measurement. Anyway, so we put our infrasound sensor there with small items of the data handling system with using the Raspberry Pi, a small onboard computer. And we at the time, so we distributed 28 infrasound sensor on the ground. This is a schematic view of the Hayabusa 2 reentry. At that time, the Hayabusa 2 reentry, so this TCM5 can escape the mother spacecraft to the another planet, minor planet, so that only the capsule can going through the over the Umera territory. So this is a map around the Umera territory, and this is the trajectory of the Hayabusa reentry. This is the landing point, and this small number 1 to 7, 8 shows our observation sites for the infrasound, and this distribution of the red color is cutting university team video camera network. So at the time, December 6, 2020, we have also the good sky in the nighttime, summer sky in December, and the distributed infrasound sensor can catch successfully for the every 28 sensor. So this is one example of the 4 sensor at the same site. So this kind of observation, we have all 7 sites, so that we can calculate the trajectory of the reentry by only using this infrasound observation. This is also the coupling observation of the seismic dataset. Then I have to change my topic onto the tsunami disaster mitigation by using, I believe it can be used for the disaster mitigation, future tsunami. As you know, 2011, we have the very, very disaster situation in the Pacific Ocean side of Japan. As the most effective region was the Tohoku region. So I experienced in the Tohoku region sea coast in my student days, so that's it was very sad thing. But the important thing is this is my photograph of the making the copy of the TV screen. But at that time, I take a trip to US, and this photograph is captured under my hotel room in near the Washington, US, and at the time the CNN TV channel broadcasting just copying the NHK Japan broadcasting company's movie without any English characters on the screen. So this is a very severe situation at the time. But the important thing is that the tsunami alert or the tsunami advisory is only shown this red region. So the alert region is smaller than we should have. It is the important problem for us to make. We should develop more good alert system. Just after that, the Professor Lai currently the Japan Weather Association in Tokyo. They operated the CTBTO infrasound observation network for the nuclear bomb test observation in the worldwide scheme by led by the United Nations. They observed infrasound at Chiba here, as well as they can access the dataset of the Khabarovsk and Kamchatka for their city video network. So they observe the very clear overpressure just after the seismic vibration on there. We have the here 20-minute scale period overpressure. Overpressure is about 20 Pascal up to 60 Pascal. It is a very, very large period and very, very large amplitude overpressure observation by using the such infrasound technique. By using this kind of information, we can make sure that this region is a tsunami source, and the tsunami source is effectively creates the infrasound signal, and this infrasound signal can reach from the sea, Pacific Ocean to the seashore, but the infrasound can propagate by sound speed, and the tsunami propagates at tsunami speed. And the tsunami speed, as you know, maybe it can reduce the speed with decreasing the depth of the ocean. So in the shallow ocean, the tsunami can make some break of the speed, but the infrasound can propagate without break to make the information for us just before coming of the tsunami. It is important thing. So at the time, they believe that this large change is coming by the lump pressure wave for the information we can get from this. And this also affect from the ground to the ionosphere, and the ionosphere can be vibrated by this kind of infrasound signal. And this is the Tsugawa-san's paper's result of the TEC, total electron contents observation, as you know, for the ionospheric plasma pattern. And we can see the very, very clear distribution of the TEC observation. So maybe as you know that we have the very dangerous situation for the tsunami, future coming large earthquake expected on the beneath the sea for the southern coast of Japan. We call it Nankai Trough large earthquake. And if it occurs, we can very, very affected from this tsunami. We live in Kochi here, so that's the seacoast region of the Kochi. All of the territories of the city and the town is distributed very, very near the seashore, so that we have to evacuate just after the sea earthquake. But at the time of the evacuation, we need to make some information for the tsunami itself. Usually, it can be used for the alert system of the governmental agency, but it can be connected with earthquake magnitude only. And so from the case study of the previous large earthquake, they can alert some magnitude for the tsunami, but it is not affected by the realistic tsunami, so that we need observation just before the evacuation. So we collaborated with some of the institute of the universities in Japan to make the collaborative consortium for the infrasound study. And this kind of observation network is coming from the many aspects of the infrasound. Someone tried to make sure the infrasound just near the Sakurajima or the Kirishima volcanoes. We try to make the tsunami disaster mitigation. Another team can make the Mount Fuji or make another collaboration with the Hokkaido team is also the volcanic study. So this distribution of the observatories consists of the many kind of observatories, but we come together with this kind of data set exchanging in our nation to make the high accuracy tsunami warning system. Such activity is very recently, but the infrasound study is coming up from the very old history, almost 1 century or more ago. Firstly, this diagram shows us the 2008 observation, and this name Whipple is maybe the famous scientist for the comet study. He shows that this pressure observation observed at 1908, the Tunguska event in Siberian territory is something like the meteor or the meteorite or the fireball event just onto the atmosphere. Another topic is this is coming from the Professor Sida at the time of the Kyoto University. This is very large system of the pressure measurement, and this can catch this signal. This signal is coming up from the Southern Pacific Ocean at the time. So, as you know, the 1950 days, we have the atomic bomb experiment coming by the U.S. Air Force, and they got the observation, the shock wave coming from the nuclear bomb at the Bikini Islands to the Shionomisaki station, Wakayama, at the time of the. They say that the signal is coming up same time, 7 Japanese time, because of they take the experiment at the same time at another day. Our schematic view of our image of the observation for the tsunami mitigation is like that. So tsunami is coming up just after the sea bottom changes, and the water surface can change something, and this can make some loudspeaker here for the 100 kilometer scale, very large loudspeaker there, and the speaker can shake the atmosphere. Then the sound can propagate faster than the real tsunami coming up. So if we have the sensors here, so we can catch some information of the tsunami just before coming to the tsunami. But we need very high sensitivity or the very large period observation of the infrasound. So we developed this kind of sensor up to 1 millihertz. It means that the 1,000 second period of the infrasound, and the minimum sensitivity level is 1 millipascal. It is successful, and we distributed this kind of sensor network in Kochi region. I believe that the arrayed observation is very important. So this scale of the tsunami observation, this scale size is almost 20 kilometers from the Muroto to Aki, Toyo. So changing of the 20 kilometer means that as you know, the sound speed is almost 0.3 kilometers. So that's 1 kilometer, 3 seconds. 10 kilometers, 30 seconds. It means that this is 1 minute change from Muroto to Aki. So we can measure the difference of the time of the arrival of the large scale infrasound by changing the 1 minute phase change of the observation, I believe. After establishment of this kind of network, we observed some of the event of the earthquake or any other. But we don't have the large earthquake, fortunately, so that we don't have such data set. This is a case of the earthquake study, but not so large. Magnitude 7 is large, but not so large for the infrasound observation. So we can make some shaking on the surface of the ground and make some small changes just after that, but not so much, not so large. So this is we cannot make sure such, but only the small fluctuations there, so we can estimate the magnitude of tsunami itself, and our tsunami magnitude calculation shows that the magnitude 7.0, it is almost consists of the magnitude of 7.3 earthquake magnitude, but it is unknown because of the fluctuation is very small with respect to the noise level by the weather situation. This is comparison with large fluctuation for the Tohoku large earthquake with small fluctuation we got just after the magnitude 7.3 earthquake. So these small changes consist of the small scale infrasound, and this large amplitude is coming from the large earthquake. It's very, very effective for the observation, but this small scale is almost a noise level, as you know. This is the case study of the Mount Sakurajima eruption, and this is observation of the observatory in Kochi region. So we have the first signal coming up for the western side of Kochi, and this is the most eastern side of Kochi. We have almost 150 kilometers or the 200 kilometers from the westernmost and easternmost territory in Kochi, and this from this kind of observation we can make sure the how to get this kind of wave from the erupted of the Mount Sakurajima. We have to make sure that our distribution of the temperature or our distribution of the wind speed in atmosphere, at middle or upper atmosphere, to make some uh, route of the infrasound in the atmosphere. Another study is coming up by using this three-station network of the infrasound study for a couple of years there. At the time, we have many Sakurajima black neck eruptions, so we can make sure the sound source detection by only using the infrasound. Another topic is the typhoon. The typhoon can affect the infrasound also, but this case of the Muroto Cape is affected by the direct attack by the typhoon. But at the time, so we can see the typhoon attacks the Muroto territory very effectively. But just before, the adjacent, just near the observatory, the Aki is located almost 20 kilometers apart from, affected not so much. And if the 100 kilometer scale, we usually takes such vibration as a high wind situation, but the typhoon affect only the Muroto Cape at the time. So this is a typhoon case. But for the, as you know, maybe you remember the Tonga eruption of the volcanic eruption, very rare case. So maybe it is 100 years scale of the very rare event, the Tonga event. At the time, so the infrasound can propagate from Tonga to Japan. And this is a data set of awards from Taiki Town, Hokkaido to Kumano City in middle of Japan. Then the another data set from the Kochi territory to the Miyazaki territory, Kyushu Island. As you know, as you can see, we have the very coherent signal from Hokkaido to Kyushu at the same time, almost same time. It means there's the same sound or the infrasound coming from the Tonga volcano to the worldwide propagation. This distance from Tonga to Japan is almost 8,000 kilometers. At the time, we can see such very effective wave form, and it is very rare event, and we take the very rare event for the tsunami, a small scale tsunami shaped by this kind of atmospheric wave. So at that time, atmospheric wave can touch and the sea surface can be vibrated by the infrasound. So that some small tsunami coming up Japan sea coast. At that time, from the Hokkaido to Kyushu, we have the 310 meter per second LAM wave first catch up. Then after that, acoustic wave, two types of acoustic wave of the propagation passes. One is propagation mesospheric or the thermospheric propagation. Another one is stratospheric condition. So it is some cases of the bouncing of this is stratospheric reflection, and this is thermospheric reflection. Two cases of passes can be calculated. And then the other one is the atmospheric gravity wave here. And the important thing is that this atmospheric gravity wave just after the sound can touch the ground, it can touch on the Pacific Ocean surface, can vibrate the uh, small tsunami at the time. This is a spectrum observation, and this is Lam wave first touch, and this is acoustic wave of the two category, and finally the gravity wave can vibrate the sea surface. Okay, so almost 1 minute left. I can show you the final one for our small infrasound sensor on board the balloon of the student balloon campaign in 2017, launched from Sweden, as well as we have the launch of the small sounding rocket by Japanese company Interstellar Technologies. We have also the infrasound sensor on board this sounding rocket. But it is some photograph on board. But unfortunately, we have the failed of the launch at the time. But we have the pressure for this kind of explosion. So we can estimate this kind of energy, and it is not so large like this images. So this is our observation at the time. Then after that we have successful launch the rocket to the 100-kilometer space, and we got this kind of data set. Okay, so from my introduction, my name is on this number minor planet. So my dream is making some small spacecraft to this minor planet by using their future rocket technique. Okay. So summary is there. So I think I believe the infrasound technique is very important to focus on the geophysical study, as well as future disaster mitigation of the tsunami or the small scale geophysical event like the landslide or something to be affected our life. Okay, thank you very much for attention.
Yeah, thank you very much for this nice talk. So, anyone has questions from audience, or you can type in the chat box. Or let me start. I have several questions.
Mm-hmm.
So you have some limitation for the location for where you put the sensor.
Mm-hmm.
Just if you want to detect the tsunami, so where
Mm-hmm.
you put the sensor on near the coast or somewhere.
Okay. Okay. So here we have the distribution of our sensor network, and this color. Please wait. This color orange circle shows the hours of battery. So hours of battery distributed from Hokkaido to Kyushu, but halfly distributed in Kochi region.
Mm-hmm.
So for the large scale tsunami coming up like this, we can cover from the Kyushu to Tokyo region, we can cover. But if we have the small scale infrasound, like the fireball or the landslide or volcanic eruption, so it can propagate small scale. So for the landslide case, maybe we can only hear the sound in the region of a few tens kilometers.
Okay.
So such small scale we need more sensors. Small sensors is enough for the detection, but we need much more sensors.
Mhm.
For the tsunami, I believe so. This distribution level is enough for the Kochi case. But for this region, we don't have any uh, infrasound sensors, so that we believe that if we distribute infrasound sensors for about 1,000 or the 2,000 sensors in our nation, like the GPS network or the seismometer network, it is enough for all of the cases.
Thank you.
And for your information, uh, can you see this small sensor by my camera?
Yes.
Okay, so this is MEMS type, MEMS type sensor of the pressure sensor. So it can measure the atmospheric pressure level like the 1000 hectopascal for the weather information. This can measure roughly, but it is very cheap sensor for the infrasound. So in our project, we will distribute these sensors for the 100 scale. This is almost all the sensors to be distributed in the Fukuoka region, one city. So please imagine the one city, we have the 100 infrasound sensors or the pressure sensors there. So it is for the disastering mitigation for the weather, severe, heavy weather condition like the flood or the landslide.
Mhm.
We are trying to get there in within a few years.
Yeah, another question is about what is the benefit if you put your sensor on the balloon?
Okay, so the balloon or the sounding rocket can be used for measuring the upper atmospheric study. As you know, that we have the distribution of the sound speed or the temperature distribution of the stratosphere, mesosphere, thermosphere, as you know. So we have the reflection from the atmosphere, thermospheric reflection or the stratospheric reflection, like this. So the sound cannot propagate straightly on the surface or along the surface. So the sound can emit the sound source on the ground, but it can make a spherically distribution, and then going to the one sound wave can reflect it upper atmosphere again, then getting onto the ground. Then the reflection on the ground surface then to be propagated another. So this kind of very complicated sound paths we can measure, so that the direct measurement on the stratospheric condition is very important. For the cases of the Hayabusa or the Osiris-Rex re-entry recently, we tried, US people tried the balloon observation at the time of the re-entry, so that we can make the observation like this on the ground, as well as we have the if we have the small sensors on the balloon, so we can identify the real observation of the multiple path effect.
Thanks. So this is why, because you in your slide you said you detected the Tonga eruption
Ah, mm,
in the same time in Hokkaido and Kochi.
yes.
So this is the reason because the the wave are not propagated directly.
The question is the propagation process of the.
Yeah, yes, yes.
Yeah, okay. Yeah, okay. So as you can see, firstly, we have the web here. We call it LAM web. LAM web is something like the surface web on the Earth. But imagine our planet is the radius is 6,000 kilometers, and atmosphere is a very thin, narrow layer. So that's a small atmospheric region is we can the LAM wave propagation there. So it is surface wave.
Mhm. Yes.
If we imagine that atmosphere is a very large region, so that it cannot be imagined. But if we imagine the planet and very shallow atmosphere there, so that this is surface wave,
Mhm.
and the acoustic wave catch up after the LAM wave. This sound speed is almost 20 uh, 280 meter per second because of the acoustic wave can propagate upward, then reflected, then the on the surface also reflected. So multiple reflection of the acoustic wave can propagated from the Tonga to Japan at the time because of the sound source is very large, and
Mhm.
we have the spectrum study so that the acoustic wave consists of two patterns. One pattern is here and second pattern is here. So we uh, simulated the propagation of the sound. Then we found that the stratospheric reflection and thermospheric reflection we have. So this is we can have the two kind of spectra. Then finally the gravity wave is caught after the acoustic wave. This is 250 meter per second, very slow wave coming up after the uh, acoustic wave. As you know, as you can see, this fluctuation is very continuously, and almost the same period signal is continuously here. So it can make some uh, shaking on the ground surface or the sea surface. And if we have the ground, so not so much effect, but on the sea or the Pacific Ocean level, so it can make good timing, good period for the shaking vibration. And it can make some small tsunami just before the coming up on the seashore. It is almost centimeter scale, 50 or 40 centimeter, but it can make some effect of the uh, uh, structure of the port, so it can affect the 1.3 meter tsunami. There.
Yeah, thank you very much. We thanks Professor Yamamoto again. Yeah, thank you very much.
Thank you very much. So, if you can come to the Kochi or the southern part of Japan, so please call me.
Sure.
Yeah. See you.
See you.
Thank you.